Benjamin Guedj has been Principal Research Fellow at UCL since 2018, and that's in parallel with the job as Tenured Research Scientist at INRIA. And he spends a bit of time at the Alan Turing Institute in London as well. And his PhD thesis was 2013 from the Sorbonne and joined with Telecom. So he works on statistical learning theory, and in particular on this PAC-Bayes setting that he's going to talk about today. A number of his results consider neural network architectures and what's possible for those. He describes himself as obsessed with generalization. And I guess I'll also say it's fitting that he shares a department, even an office sometimes in London with John Shaw Taylor, who's the person who originated this PAC-Bayes framework. So we're going to hear first about, the general details of PAC-Bayes, and then we're going to get an update on news from the field. So I'll let Benjamin talk now.
Thank you very much, Mary, for the very kind introduction. Let me just try and share my screen. All right, is this working? Can you all see my slides?
Yes.
Okay, fantastic. So I'll start. Thank you very much for the invitation. I'm very delighted to be speaking with the LMS today. Thanks, Mary, for the kind introduction. As you said, I originally started in mathematics, so it feels a bit like home being at the LMS today. I'm very happy about that. I've been masquerading as a computer scientist for some years now, and I'm now sitting in the computer science department in the Center for AI at UCL in London, so we're based in High Holborn. Also briefly mention this INRIA London program initiative. This might be of interest to some people in the audience, in particular, if you have plans of collaborating with France and with INRIA in particular, please do get in touch. My research, as you just said, Mary, sits at the crossroads of different fields in mathematics, mostly mathematical statistics. Obviously, this is my field and has been my field since my PhD, but also probability theory, machine learning, of course, a little bit of optimization. So really the topic of the day, mathematical foundations of machine learning, says pretty much it all about my research, my interest, and my expertise. Here's a few keywords also to narrow it down. So statistical learning theory, as you said, Backbase, this is the topic of my talk. Computational statistics, also sampling algorithms, as you will see, are of paramount importance in Backbase. And more recently, the theoretical analysis, so theory for deep learning. A lot of people are working that field nowadays, but this is definitely a hot topic. And surprisingly, this is pretty much what led to the resurgence of Backbase. If I wanted to be provocative, I would say that I was working in Backbase way before it was cool. It's now becoming cooler and cooler as we speak. So let me try and convince you about that. My obsession, as you also said, is generalization. So I'll start with that. I'll start with that teaser on what generalization means within machine learning and theoretical machine learning in particular. Then I'll dive to a very condensed tutorial on PAC-Bayes. This is inspired by a tutorial I gave with John at ICML, one of the leading conferences in machine learning. And then I'll finish probably in about 10 minutes or so with a few highlights of recent results. This is meant also to be a teaser for the audience. If you're interested in specific results, please do reach out. And if you'd like a full talk on those results, please invite me again. All right, so this is a teaser on generalization. My first claim would be that learning is indeed to be able to generalize. So probably you've all seen this kind of pictures. This is taken from Wikipedia. This is very classical statistics and machine learning. And the fundamental question people are asking is, what can you learn about some phenomenon, some stochastic phenomenon, only from examples? If you collect some data, what are you learning about the underlying phenomenon? And it's also very well known that if you memorize what you've seen so far and use this to project and predict what's going to happen in the future, if you collect new data, this is usually very bad. This is called overfitting. And as much as possible, we want to avoid overfitting in statistics and machine learning. So I see generalization as the opposite. This is the ability to perform well on data you've not seen yet. And pretty much on any data you might be able to collect in the future. There's been a lot of interest in generalization lately, in particular related to deep learning. There's this claim that deep learning might be breaking statistical learning theory as we know it. it is also well known that you have this bias variance trade-off between the complexity of models and the possibility really of overfitting. So for example, DeepNet, when you train them on very massive data sets, as it's done routinely nowadays, you basically achieve a zero training error, which should be a trigger alarm really for us statisticians, in the sense that it might strongly suggest overfitting, but this is not quite what is happening. So this is also a very classical picture. This is taken from a very nice paper from Misha Belkin, Daniel Su, and co-authors. This is the celebrated bias variance trade-off in statistics. And in the x-axis, I have the complexity of the family of hypotheses. I will make this formal in a couple of slides, but just think of this as the size of the model you're using to make predictions, for example. And then on the x-axis, on the y-axis is the risk. So the dotted line is the training risk, the error then you can compute on the sample you collect. And the solid line is the theoretical test risk, which is actually what you want to optimize. And again, this is also super classical, that you want to aim for that sweet spot, right? As you increase the size of your models, then the training risk will eventually go to zero, or at least to a very small value. But this is overfitting in the sense that you're mimicking what you've seen so far, and you won't be able to generalize, and you won't be able to perform well on any future data. Think of this analogy: if you memorize all the questions to a test when you're in school, and this is the only thing you do, and not even understanding your subjects, it is very likely you will fail any future test, right? Unless they have the exact same questions. This is exactly what's happening here. Misha Belkin and his co-authors have conjectured that this might actually just be one half of the picture, and this is what the other half could be like. And this is extremely exciting and stimulating in the machine learning community at the moment. There is this notion that rather than the sweet spot of optimizing between the complexity and the risk, there might actually be a second threshold, which they call the interpolation threshold. So the training risk eventually goes to zero, and the test rate goes up. But after some point, we reach what is so-called the over-parameterized regime, and then the network is indeed able to interpolate between new points and actually generalizes better. What is very remarkable on that picture is that the minimum on this right-hand side of the picture is actually lower than the minimum in this regime. So eventually, the generalization is better. And this seems to advocate for larger and larger networks. I'm only saying this seems to advocate because we're still lacking the theory, and this is pretty much where PAC-Bayes kicks in, as you will see. Another topic to try and motivate what generalization could mean also in machine learning is this notion of semantic representations. This is a jigsaw puzzle. So this is taken from another fantastic paper from Naruzzi and Favaro back in 2016. And very, very simply, this is the idea that if you use a machine to solve a jigsaw puzzle, eventually it will succeed, obviously, because it's just a brute force problem. If you give this to an infant, well, if you have a notion of what the picture actually represents, you will accelerate drastically the learning, because you will cut off many of the possibilities, many of the combinatorics of what should be explored. In particular, you will not try to put two wheels next to each other, right? You know that the top of the car goes next to a different part, and on goes to next to a door or whatever it is. So there's this notion that if you do understand the underlying representation of your data, if you have a notion of semantic coherence of your data, in this case an image, then you have a good chance to drastically accelerate the learning phase. This is the topic of a very big project I'm a member of, which is called the Semantic Information Pursuit Project, the MURI, and this is funded both by the UK and the US with a number of PIs. The local PI in UCL is John, and René Vidal is the overall PI with Mike Jordan, Arnaud Doucet from Oxford, and so on. So this is another direction in which generalization proves of paramount importance, and I will comment on this a bit later on. A last example to finish that teaser is what I like to call a tale of two learners. So let's assume I have a very simple cognitive task. I must identify items on images. Say I have images from Google Images, and I want to identify horses or cars or whatever it is. If I train a neural network, so this is very classical architecture, a feed-forward architecture with a number of hidden layers. We now have algorithms, computing power to do this on a laptop, really, and you will achieve an accuracy which is essentially 100%. You will be able to perfectly identify horses on images. This requires a lot of computing power, even though it now fits in laptops, whereas 5 years ago it didn't. But it still requires a lot of data, a lot of clean data. This is important. You need annotated images of horses. It also requires a lot of computing power, so GPU expensive, and it has a significant environmental footprint. This is a growing concern in the machine learning community. So that's contender number one. This is contender number two, the coming generalization of Backbase researchers, maybe, who knows. And for the exact same tasks, they can also achieve 100% accuracy, right? Not just because they're my children, but any children could do that. They're also very good at doing something which is out of reach for machines for now, at least on those scales, in the sense that they can transfer that knowledge to different problems. In particular, if they are able to recognize horses on images, they can also recognize zebras. They have a very good sense of coherence in the world, and that matches this notion of semantic coherence I was alluding to a minute ago. There is a striking mismatch between how many data and how many compute power is needed, really, between both learners to achieve the exact same result. So this calls for a refoundation, really, of the learning paradigm. And this is also where PAC-Bayes tried to get in. And this is very much the topical research which is being carried in my group here in London. So back to my original claim, learning is indeed to be able to generalize, but not from scratch. So we need to incorporate mathematically, we need to derive a sound theory of assessing this semantic coherence, of integrating this notion of coherence between data points and tasks in learning frameworks. So this is what I mean by incorporating structure and semantic information or implicit representation of the world, which are inaccessible to machines so far. So the hope is that this leads to better algorithm design in many sense, but in particular in the sense that they will be more frugal in terms of data, of computing power, more intelligent also in the sense that they will be able to extend the number of tasks they're able to comply. So for example, if I can identify horses in an image, maybe I can transfer this to zebras or unicorns or whatever it is. So again, if you're interested in these topics, feel absolutely free to get in touch. I'd be delighted. All right, let me move on now to the actual tutorial on PAC-Bayes. So this is John Chotella, for those of you who don't know him yet. John used to be the head of department in computer science at UCL. He's now UNESCO chair in AI, and I'm extremely fortunate to be mostly working with him in London. So this is a very condensed part of a tutorial that we gave at ICML 2 years ago, and you get the link at the bottom of the slide if you want to see the slides and the video. All right, this is a very simple setting. I'm not going to bother with technicalities at this stage. I really want to focus on the concepts of what PAC-Bayes are, and in particular, what this can be, how this can be leveraged in many learning problems. So let's assume that I have a supervised problem in the sense that I will be collecting inputs and outputs. So the training sample is the points I collect. I assume it's given from the beginning. So I call this SM. And this consists of M, I, D replications of some random variable. So X's are the inputs and the Y's are the outputs. You can think of X as an image and Y as there is a horse or there is no horse, for example. It could be anything. The beauty of that framework is that it is generic enough to capture pretty much any learning problem you could think of at the moment. H is the hypothesis class. So H is the collection of function from which I will draw some candidates. And those candidates should morally behave as, if I use this function and I feed it in X, it should give me something which is as close as possible to the Y. I will make this formal again in the next slide, but this is the idea. The only assumptions I'm making at this stage is that the collection of points I'm collecting is an IID sequence, so independent and identically distributed. They all come from the same data generating distribution P. I don't know the distribution, obviously, and basically the objective in machine learning and statistics is to try and infer properties of that distribution. So this is all very classical, but please do raise your hand if you have a question. I'll also start with a very simple claim about what statistical learning theory is about. For those of you who are not in the field, statistical learning theory, in my view, is about high confidence on statements. And I'll make this clear on this slide. Let's assume that you have a fixed algorithm, say in your network, for example. You have a fixed function class and you have a fixed sample size. You know that you will pick m points, and that's it. You could generate random samples. So I could generate m-sized samples over and over again, and I could focus on the distribution of test errors. What statistical learning theory is all about is to focus on the tail of that distribution. You could focus on the mean, of course, but that's misleading, obviously. So we're really interested on the properties of the tail of that distribution. That is, we want to find bounds which hold with a high probability of a random samples of size m. And this is really the paradigm I'm going to be addressing this morning. If you compare this to a statistical test, if you're familiar, then what you want to have are statements such as at 99% confidence level, for example, you want to enunciate a property of a learning algorithm. In the sense that the chances of that conclusion not being true are less than 1%, for example. And you will see this in the PAC framework. So the PAC framework, so PAC stands for probably approximately correct. This can be traced back to Leslie Valiant in the 80s. In the PAC framework, you typically define a confidence parameter, a slack parameter, really, delta. And this delta controls the probability of making a large error. If you take the converse, then you have this high confidence statement that is the probability of being approximately correct. And again, you will see this in a formal definition in a few slides. Then being approximately correct occurs with a probability which is close to 1, not exactly 1, but close to 1. And you control the amount of approximation, the delta parameter, because you fix that. So that's the celebrated PAC framework. What can you do from that sample? So let's assume that you've collected your sample, S of m, you have x's, you get y's. What can you do with that? Well, basically two things. You can first learn a predictor. So you can train a machine learning algorithm and learn an actual predictor, so the actual function that will map inputs to outputs. But you can also do something which is, in my view, far more interesting. You can certify its performance. You could learn any predictor from a sample. You could learn very good ones, you could learn very bad ones. What you need to do is to have a procedure, theoretically sound procedure, to certify the quality of those predictors. And this is what statistical learning theory is all about. So by learning a predictor, as I just said, you can use any learning principle. You could use prior knowledge. You could use a Bayesian inference machinery to inform your prior, to inform your prior and to learn your predictor. And by certifying performance, I mean generalization bounds, really, and what happens beyond the data that you've collected so far. All right. Yeah, and obviously, as we will say, those two goals interact a lot with each other. It's the interplay between both, really, that makes it, in my view, very interesting. So here's the formal definition of what generalization is, as promised. I'm going to use, again, very classical notion and notation from decision theory, information theory. So let's assume that I have a loss function L, and this loss function only measures the discrepancy between two elements, the actual output and the predicted output. So Y is the true output. H of X is my guess. I have X, the input, and my guess is that H of X is a good approximation of Y. In what sense? Well, in the sense of the loss function. So that loss function is just something that returns a scalar, typically a positive number, which is a measure of discrepancy between both. You could think of, for example, the square distance. But the square distance is one of the most used loss functions in machine learning. Because X and Y are random variables, obviously L of H of X and Y is also a random variable, so you cannot compare directly to the two values of the loss function, but rather you can compare the expectation of that loss. So this is the theoretical risk. I will call this R out for out of sample. And the empirical counterpart is the empirical risk. So it's just the empirical average over the sample. You can't compute that number, the R out, but you can compute this one. And as you will see, this is a metric which is essentially used in pretty much all machine learning works to some degrees of refinement, but this is really the backbone of what people are doing to assess the quality of a predictor. The question we're asking is, if I have a predictor H, which does well on the in-sample pairs, so the sample we've collected, will it still do well on out-of-sample pairs? In other words, if R in is a small number, does that give me an assurance that R out will also be a small number? That's all what generalization bands are about. And so for that, we define the generalization gap, which is simply the difference between the two. And the upper bounds that we can derive on generalization gaps will say that with high probability, this difference will be upper bounded by some term which will depend on the confidence delta. This holds with probability at least 1 minus delta, as you recall from the previous slide. It will also depend on the sample size. It will depend on the complexity of the problem, on some properties of the data generating distribution, and so on and so on. And this comes in a number of flavors. So by distribution free or distribution dependent, I mean that those bounds could be specific to assumptions on the data generating distribution. If I'm keen to have a statistical model, if I want to assume that Y is a Gaussian transformation of the input plus random noise, for example, then this gives me a distribution dependent bound. If I'm not willing to do so, then I'm just assuming that there exists a probability distribution, which is the underlying data generating distribution, but that's it. I don't constrain in any way the form of that distribution. It also comes in algorithm-free or algorithm-dependent flavors in the sense that this could hold for a specific H. H is your favorite predictor, say a linear regressor or neural network or a Bayesian predictor, or this could hold for any H. And as you will see, PAC-Bayes is most concerned about this generic case where you can actually have a bound holding for any predictor because, and probably you all see me coming, if it holds for any predictor, then you can optimize for it, hence the connection to optimization theory. Right. So this is, again, a formalization of what I've been saying earlier on the PAC framework. So the probably approximately correct. Now you know all the terms. These blue terms over here are the generalization gap. So R out minus R in is this delta quantity I had on the previous slide. This is the generalization gap. I want this term to be small. This is the right-hand side of the bound, which is the control really that I have on the generalization gap. And this occurs with high probability. So if I read that equation, then that's inequality. Then with high probability, the red part, the generalization error of any hypothesis H, the blue part, is at most the green part, something that I can control. And this term is the one that we're going to be massaging in a few slides. So if you can control this term or even compute it, which is the most favorable case, then you get what you call a PAC generalization band. It's not PAC-Bayes yet. So you can think of this as more really a complexity of your problem, as I was saying. It will decrease with the sample size. It will increase as you put your confidence parameter delta smaller and smaller, of course. If you want this to hold with probability exactly 1, then this term blows up. And what you end up with is basically the generalization gap is almost surely upper bounded by the infinity, which is true, but not very useful, right? So this is all about those high confidence statements on the tail of the distribution of the test errors. And again, keep that analogy with the statistical test in mind. So this is PAC. What PAC-Bayes is about is basically PAC generalization bands, not for hypothesis H, not for functions, but rather for distributions of the functions. And this additional layer, this meta step really is what makes PAC-Bayes so specific. At this stage, maybe some of you are wondering whether you should care about generalization or not. Let me try to convince you. In machine learning, generalization bands are a safety check. So they give you two things. First, a theoretical guarantee of the performance on any predictor that you could compute. And more practically, they also give you how to say, guidelines on how to use those algorithms. And I will make this clear in the last part of my talk in an example for deep neural networks. So generalization bands give you a computable control of the error on any future data. The only assumption you're making is that the future data comes from the same data generalization distribution. This is for the sake of the talk. We do have exciting results which allow us to actually relax that assumption. But for now, let's just keep it this way. They can also explain why some specific algorithms do work. If you have a generalization band which is really tight, then it is a sufficient explanation of why this algorithm actually works on the data set you're working on. This can also lead to designing new algorithm, as you will see. And we've been fostering in my group the use of Backbase as a principled way to create new machine learning algorithms, not just analyze them. The take-home message at this stage is really that PAC-Bayes is a generic framework to rethink what generalization means for statistical learning and machine learning algorithms. It has a Bayesian flavor, as hinted by the name. You will see this in a minute. And it allows to create new algorithms. So this is really a principled framework which is gaining more and more traction in the community. Here's a few references if you're interested in diving a little bit deeper. So there's the tutorial I was just mentioning. It has a companion paper published in the Proceedings of the French Mathematical Society. It's the little sister of the LMS. And we have this workshop at NIPS, which is called NeurIPS, one of the leading conferences in machine learning with ICML, called Almost 50 Shades of Bayesian Learning. So you get all the talks, in particular, 2-hour tutorial from François Laviolette. As I was saying, if you're interested in the topic, please get in touch. We get a number of positions from PhD to full prof to visiting researchers. So now is the time to get excited about Backbase. I've been working on Backbase for 10 years, and the enthusiasm was certainly not the same 10 years ago. So no, I'm taking a little bit advantage of it, I'll admit. This is my final slide before actually defining what Backbase is, just to give you a sense of what generalization bands look like if you're not resorting to Backbase. So those results are from the 80s and 90s mostly. They are classical in the statistical learning community. If you have one hypothesis, so it's obviously not a very realistic case, but let's assume that the collection of functions for the prediction is just one function, say a linear predictor, then you have straightforwardly this kind of generalization bound. That is, with probability larger than 1 minus delta, the generalization gap is at most the square root of log of 1 over the confidence divided by the sample size. So as you increase the sample size, this term goes to 0 for fixed delta. And so this goes to 0 at rate 1 over square root f. This is consistent, by the way, with what is known also in probability theory and the central limit theorem. This is basically an application of the central limit theorem. If you have not just one hypothesis, but a finite set of hypotheses, then it's easy to see that so it's a worst case approach, but it's easy to see that you basically pay how many functions you get in that set. If you get a non-countably infinite function class, then there are more sophisticated notions such as Vapnik-Chovanenki's dimension, the Rademacher complexity, and so on and so on. I'm not going to dive into details because I only have 1 hour. I'm already a little bit behind time, I see, so I'm going to speed up. But the take-home message is that these approaches are suited to analyze performance of some functions, individual functions in a sense. They take very little account of correlations between different functions, in the sense that if I have a linear predictor, but just next to it, I have a different function, which actually might have similar performance in terms of prediction, in terms of the generalization gap, those techniques and those approaches will very likely miss it. What PAC-Bayes is about is integrating correlations between the hypotheses, because we consider distributions, we're maintaining distributions over the set of hypotheses. So here we come, PAC-Bayes. What are the main differences between PAC-Bayes and Bayesian inference? I've been very mysterious about the Bayesian flavor of PAC-Bayes so far, but you hopefully will get this in this slide. This is my, in a nutshell, slide to highlight the differences between both. In Bayesian inference, you usually define a prior, so probability distribution, which encapsulates some knowledge about the parameters or the predictors. It could be informed, uninformed. You could have flat priors and non-flat priors, very, very big. Pretty much everything is possible. You also resort to a statistical model. This gives you likelihood function. For example, the example I gave earlier, if I have a model in which the input is Gaussian, there's a random noise added to it, then the output is Gaussian with a certain mean and certain variance. And so the problem boils down to identifying those parameters. You get a likelihood function, the Gaussian density, for example, and then you have a unique way up to a constant from the prior and the likelihood to go to what's called the posterior, which is the main object of interest in Bayesian inference. In Backbase, the salient difference is that it is model-free in the sense that there is not necessarily a statistical model. We only use a loss function. So you could argue that some loss functions actually yield statistical models. That is true. It is not always true, though, in the sense that the model might not be explicit, and you might not even need to make assumptions which would be required, for example, in Bayesian inference. I'm thinking about assumptions such as the tail of the data distribution is not too heavy, for example, or the input is bounded on some domain. This is not required in the Bankbase approach. So this is why I call this model-free approach. What it shares with Bayesian inference is the Bayesian update principle. So we get a measure reference. So I will call this a prior and a posterior to be consistent with what's happening in Bayesian literature, but it has nothing to do with the actual Bayesian priors and posteriors. This is any probability distribution, which could resemble some of the priors used in Bayesian statistics, but it's not needed. It's any distribution on the set of predictors. And I see this as a way to explore the many possible predictors, right? So if you want to favor, for example, some desirable property, if you want to favor sparsity, for example, then you can just encode this in the prior. And the posterior is given by the multiplication of the prior and the loss function, so the Bayesian update principle. And this distribution is just the twisted prior after confronting with the data. This is your prior knowledge on what your ideal predictor should be. And then you go out, you see the world, and you collect some data, and then you twist your initial beliefs and your initial prior to really match what you've learned with your data. So that this is the main difference between Backbase and Bayesian inference. I'm just going to update slightly the notation because Backbase is all about distributions and not hypotheses. I'm just going to update the definition of the risks. So the in-sample risk of a distribution Q, so Q is no probability distribution over the set of predictors, is just the expectation with respect to Q on that set of predictors, right? The same for the outer sample risk. So it's just, I'm just integrating with respect to those distributions. Because I want to compare distributions, I need a proper notion of discrepancy. Most people in Backbase use the Kullback-Leibler divergence. You will see in the last part of my talk, if I ever get there, that there are actually a lot of strategies to alleviate this and to mitigate the role of the KL. So very quickly, the main difference is that in Backbase, the bound will hold whatever the prior. It's not the case in Bayesian inference. The choice of the prior is essential. If you pick a different prior, you will end up with a different inference mechanism at the end. The same for the posterior and the same for the data distribution. So Backbase is a very generic framework in which we want to have bounds which hold whatever the prior and whatever the posterior. And that opens the way, that paves the way really to optimizing with respect to those quantities. Here's one of the most known classical Backbase bounds. So this is due to David McAllister at the end of the 90s. And it says that with a probability which is arbitrarily close to 1, and any posterior distribution Q, so any distribution on the set of hypotheses, the generalization gap is at most the square root of the KL between the posterior and the prior divided by the sample size, plus, again, the confidence term. This always appears. So this gives you, so this, again, one of the very first Backbase bounds, the advantage of considering a distribution on hypothesis rather than just one hypothesis is that it gives you a full characterization of the overall complexity of your problem, right? You now have the square root of the KL in the right-hand side. And this gives you a measure of, is your learning problem really hard, or not. This depends on the value of that term, the complexity term, as I called it a few slides back. Let me now touch on this notion of creating new algorithm. We've been developing, we were not the first, but we've been actively developing in my group this idea that Backbase can be used to create new algorithms. So Backbase driven learning algorithm. Basically, all Backbase distributions have this prototypical form with a certain probability, and for any distribution Q, the error on the unseen data is supplemented by the error on the sample that you can compute, obviously, because you collect the sample and you choose the loss function, and a complexity term. So if you're able to either compute or approximate the complexity term, this defines a very principal strategy to create new algorithm. What you do is you simply optimize for Q in the right-hand side. By doing so, you have the Q star distribution, the optimal distribution, provided it exists and is unique. Let's assume this for now. Then you get the probability distribution, which gives you the tightest generalization bound error. It's an optimization problem. This can be solved or approximated by many techniques. I mentioned earlier, sampling algorithm, such as MCMC. I've been working on this during my PhD. More recently, SGD-based methods, Bayesian and inference are all very popular. Interestingly, very classical algorithms in machine learning, such as SVMs, regularized AdaBoost, all the exponential weights are all minimizers of PAC-Bayes bounds. Those algorithms have been found way before PAC-Bayes was even invented by the end of the 90s. But interestingly, this closes the loop quite nicely, I think, in the sense that those algorithms have found an additional justification by being minimizers of PAC-Bayes bounds. And this is why I'm talking about an integrated theory of PAC-Bayes learning. And this is pretty much what we're pushing here at UCL. I'll close that tutorial part with one proof. I mean, we're all mathematicians, so I couldn't resist. This is a very simple proof, yet extremely powerful and extremely elegant. This has been due to Shizar and Dunstan Varadhan independently in the middle of the 70s. The formulation I'm giving today is due to Olivier Catoni, one of the funders, really, of the PAC-Bayes fields. And it's about the variational definition of the KL. So let's assume that I have a function phi. I have those two statements. The log of the integral of the exponential of phi with respect to the prior distribution P. This is equal to the sup of the integral of phi with respect to any distribution Q minus the KL between Q and P. And this holds for Q absolutely continuous with respect to P. This is a result which has been used in probability theory in many fields and over the decades. What is interesting is the second part of the statement in machine learning. It gives an explicit form for the supremum. The supremum is rich for a distribution which is known in mechanical statistics, for example, at the Gibbs potential or the Gibbs distribution, which is simply exponential applied to phi and renormalized, of course. So this is a density, the Radon-Nikodym derivative exists, and this is a density of G with respect to the prior P. So this result is absolutely central, and let me convince you of this in the next slide by giving you the very schematic proof. This is just the two statements, the first part and the second part. So let's start with the Q, which is absolutely continuous with respect to P. I'm just writing what the minus KL of Q and G, G being the Gibbs distribution, is. I can artificially introduce these DP terms over here. The Radon-Nikodym exists both for Q and for G, so this is a licit operation. This is just the definition. Now I'm separating the log. See, this is definitely not rocket science here. I'm just separating the log, and then I'm writing what the density of G with respect to P is. This is given by this expression. So I'm just writing down the terms. I end up with a KL minus KL of Q and P plus those terms, which is directly given by the form of the density of G with respect to P. The only argument of the proof is to remember that the KL is non-negative. So the function that maps Q to minus KL of Q and G actually reaches a maximum, and this maximum is equal to 0. And this is reached obviously in Q equals G, right? Just writing this, and boom, there you go. This is your result. This is called a lemma in Olivier Catoni's book. this is a fundamental theorem really used in back-based learning. This is the cornerstone of most of the proofs of Back-Bayesian generalization bounds. Now, if I pick a specific phi function, for example, if I pick phi to be some, let's call this a temperature parameter, but I can elaborate on this if you have questions. If this takes the form of minus temperature times the empirical risk, then the Gibbs distribution is this term, exponential minus temperature times empirical risk times prior. So if I have a small empirical risk, this term will dominate. If I have a large empirical risk, this term will be small. So you give more and more weight to hypotheses which have a small empirical risk. This is legit, obviously. And the theorem gives me that this is the argument of the infimum of this quantity. And for those of you who've been, for example, in statistics using regularization strategies, this is exactly what you would do if you wanted to regularize not predictors, but distribution of the predictors. You want to penalize, and you penalize in the sense of KL. All right, let me speed up. This closes the tutorial part. What you've seen so far is that statistical learning theory, as I said, is all about high confidence control of generalization. Backbase is both generic, it works for any learning problem, and powerful, as you will see for deep neural networks. In some settings, it's the only way to obtain state-of-the-art results, to derive generalization results. It also serves to invent new learning algorithms. It has a Bayesian flavor as a trend Bayesian. I find this especially appealing. And what's interesting is that it mixes several tools from mathematics and computer science, in particular statistics, probability theory, and optimization. And as I was saying, this is, to date, the resurgence of Backbase really is 4 or 5 years ago, when people realized that it's essentially the most promising way to analyze the transition properties of deep neural network architectures. Right, what's coming in the few minutes I have left is what we've been up to with Backbase. So this is a sample of exciting contributions and papers that we've done in my group in the past 3 years. It goes back to 2018. In the interest of time, I'm probably just focus on one, which is the second one in bold, this dichotomized and generalized Back-Bayesian binary activated deep neural networks. This was a NeurIPS paper. I'd love to comment on obviously all of those. This is obviously not possible, but I'm very happy to give pointers or engage discussion if any of you is interested in those papers. But as you can see, this spans quite a large range. This supports the claim I just made that Backbase is indeed extremely generic. You could tackle supervised learning, unsupervised learning, ranking. We have core contributions on theory, on the theory of Backbase, really using new concentration inequalities, for example, as in this paper. There's a connection to contrastive learning, which is at the core of self-supervised learning, which is all the rage now. There's also openings towards different measures of the risk. For example, using the expectation of the loss is something which is extremely convenient. Mathematically, it does not make sense in many applications. If I want to assess the efficiency of a vaccine, for example, I don't want to focus on the mean efficiency. I just want to make sure that I don't kill anyone. So this asymmetry of the loss function is very little captured in the existing theory. So we have contributions in that direction as well. Other directions in deep learning, in particular on generative models, which is probably the most recent work on this slide. So all of this is forming, I think, a very vivid community and very active fields of research. I'm also extremely fortunate to do this with a fantastic bunch of people. I'm not going to cite them all, won't have time, but those are the many faces of the Backbase experts in the world, and they're all fantastic people. Some of them are in London. All right, so I'm just going to skip that. This is an extension of the Backbase theory to the case, as I was saying earlier, that you don't necessarily have a bounded signal, or you might have heavy tails and so on. But in the interest of time, I'm just going to comment on this binary activated neural networks contribution. This is a super classical architecture as before. It's a fully connected forward architecture. The only thing which is a bit odd is that we're using an activation function, which is not the ReLU or the sigmoid or pretty much all the activation functions people are using nowadays, but it's this sign function. So what's happening in that network? I have this layer of inputs, and then all the neurons I have in my network, I have this sign function. So from their inputs, they only output +1 or -1, depending on the sign of the inputs. I can mix this with weights, and so overall, the output of my neural network is this f theta quantity at the bottom of the slide, which is just the composition of the sign function applied to, so the wi is the weight matrix for the layer I. I have capital L layers, but again, don't pay too much attention to notation. What's important is the concept here. So this is the way I can write my neural network. And we have that trick, which is specific to Backbase. So before that contribution, there was basically no way to have a theoretical guarantee on the generalization of this kind of architectures. This kind of architecture, by the way, is appealing. I mentioned earlier the environmental footprints of machine learning. If you only need to store +1s or -1s at each neuron, you could see the computational savings that you will do, in particular in terms of storage. So this kind of architectures has been explored by the industry in particular to try and diminish so not always the environmental cost, probably just the cost, but a corollary of that is also the environmental cost. So the trick that we have with Backbase is that because we're not interested in the prediction, but rather in a distribution of the predictions, you can also take the expectation of that neural network. And if you take the expectation of the network and you pick your prior and your posterior distribution to be very specific, in this case, Gaussian distributions, then what's in red over here is the cornerstone of that paper. Basically, the prediction, the expectation with respect to the posterior of this network with a sign activation function behaves like a function that we know very well, the F function. And because we have an explicit form of the prediction, then we can just use the PAC-Bayes machinery to analyze the performance of that predictor and analyze the different trade-offs between the prior, the posterior, the way it changes the weight, and the way it changes the generalization. I'm just showing you the building block for just one layer. So one layer is not really an interesting neural network. It's basically just a linear predictor. But this is the building block that we leverage afterwards. And then we extend it to an arbitrary number of layers. So the results we have in that paper hold for any neural networks with that kind of architectures with capital L layers. L could be anything. As soon as it can fit on your laptop or your cloud, then you can use it and you can benefit from the PAC-Bayes theory to understand its behavior. This is a generalization bound that we managed to develop for that network. It's a simplified version. Again, I'm not going to comment too much on this one. What's important is that we still find the same ingredients as before. Again, this unified theory of PAC-Bayes behaves the same way, basically, if you have a linear predictor, a decision tree, random forest, or a complicated neural network, you still get those three colors: the blue part, the red parts, and the green part. And the green part is the complexity. This captures the complexity of your network, and this matches similar results also in information theory. I'm just going to close with this slide right on the hour. So it's almost exactly 50 minutes. So I'm just going to stop in 1 minute. The numerical experiments that we had in this paper, I'm just going to focus on that last column. Let me zoom in. So this is for MNIST, which is a very classical baseline in the machine learning literature. It has been for decades now. Those three columns, so this is the architecture that we have, Bayesian net, so PAC-Bayesian gradient network, as we called it. And you get three columns: the in-sample risk, so your performance on your data set on MNIST, the out-of-sample risk, which is what you want to minimize, but you never observe it in the real life, and the value of the band. So this is the PAC-Bayes band. I said earlier that generalization bands are not only of theoretical interest, but they are also practical guidelines to practitioners. And this is very much the vision we would like to convey. Even if you're not interested in Backbase or statistical learning theory, if you're using a deep neural network for any kind of problem, you might be interested in having a certification mechanism given by Backbase. And this is what we provide here. The way you should read those columns is if on that particular instance of the MNIST problem, I have a 1.8 error rate on my sample, the bounds, when I compute the exact time of the bounds, I get a 3% error rate. What this means is that this is computed with confidence of 0.01, meaning that with probability at least 99%, if I have new points coming from the same data set, the error will never be larger than 3%, right? So you don't even need to collect your data and compute the error. The theory gives you that with probability larger than 99%, you will never have an error larger than 3% if your initial error was 1.8. This is what I mean by certification mechanism. You can now certify, we call actually this a self-certification, in the sense that you're using the exact same data to both train your network and then compute the Backbase generalization bands. And that gives you theoretical guarantees on how your network is behaving and will behave in the future. All right, I'll close here. This is an attempt at summarizing what I've been talking to you about. So as you probably all got, my obsession is very much this quest for generalization guarantees through PAC-Bayes, not only, but mostly through PAC-Bayes. And the few directions I've mentioned, so the fact that we have bounds which are more and more generic, bounds which are tight for some specific settings, in particular for deep neural networks. We have new measures of performance. I briefly mentioned asymmetric losses, quantile losses, ranking, contrastive. This is all extremely active in machine learning. And this idea of coupling theory, I'm a theoretician by training, and I'm very happy about that. But the tendency in machine learning right now is very much driven also by applications and spectacular successes, empirical successes. There's no way in denying that. So what I find interesting in this line of research, in Bankbase in particular, is that it brings together really theory and the algorithms, and can shed some light on some empirical successes with a number of applications that I mentioned already. All right, thank you very much. I'll stop here. If you do have questions, please reach out now or after offline. And this is also a few pointers to some other papers if you'd be interested in extending the conversation. Thank you very much.
Thank you very much, Benjamin. So I've got a question of my own, but there's also one that has come in from the audience. So I'm going to let Guedj speak when I just give that option to him.
Yeah, I got the option.
I have done that. Mary.
Thank you very much. Okay, Guedj, you can speak now.
Yeah, hi, thank you so much for your talk. I am just starting my PhD at Oxford University. So I am interested in learning more about this. One question that I had was between PAC-Bayes and information theoretic bounds, which one do you think has better scope to sort of generalize towards deep learning? And are there ways to unify the two together?
Thanks very much for that question. It's extremely timely because we do have ongoing projects to try and match the two communities together. There's a lot of tools which are actually common between information theory and Backbase. There's a few papers, so I don't have any listed here, I'm afraid, but I'm very happy to give you pointers offline. There's a few papers exploring really what is the connection between classical notion of information in information theory. I'm thinking about, for example, the mutual information or conditional mutual information between data sets, how you can map that to the actual levels of complexity that you would get from Bankbase. If I go very briefly back to actually the part I've skipped, which is this new Backbase bound with F divergences rather than the callback libeler. So this is a strict generalization of the callback. The callback is just it's just an F divergence with x log x as the F function. We have a few pointers in that direction trying to match this with quantities directly narrated by conditional mutual information. I don't know if that makes sense. But in particular, we have an ongoing PhD project which started. If you're interested in joining the reading groups or the discussion, you're most welcome.
Yeah, that would be great. I'll probably message you offline.
Absolutely, absolutely.
Sounds good.
Thanks for your
Jenny.
question.
I'll ask a question, and it's maybe influenced a little bit by the fact that I haven't been following all this PAC-Bayes literature, but you have this concept of the distribution over hypotheses.
Yeah.
And as a consequence, you know, a lot of the kind of concrete results with respect to particular machine learning models, they tend to be, you know, over a distribution on the weightings and the parameters of those models. So I'm just wondering, you know, if we're dealing with kind of real life neural networks, how likely is it that de-randomization can be, you know, kind of, I know you have some initial results, but how far do you think those can be pushed to get, you know, realistic answers that will kind of link more to, you know, actually the design of specific neural networks?
Yeah, that's an excellent question. Thank you. There are two things really. For a long time now, people have been introducing randomness in the way they train neural networks because they've observed empirically that it would yield better performance, in particular, better generalization performance. If you think about it, dropout is nothing more. Generalization of the weights is nothing more. It's exactly what we would do in more classical statistics, for example, when you penalize, you know, properties of your parameters. For example, when you do lasso, you're doing exactly that, or ridge regression. So this has been known by practitioners of deep networks for a long time. I think what is developing now is the theory trying to understand what are the benefits of randomization. And if you slightly perturb the weights of the neural networks, there's a number of exciting questions that arise. For example, is it robust? If I slightly perturb the initialization of the weights of my neural networks, does it give me the exact same network at the end? You know, if the answer is no, then probably the way you train your network is not very robust to small perturbations. So there's an entire theory on this, leveraging the notion of stability, on which we also have a few contributions in my group. There is also a movement, in particular in Backbase, trying to understand the benefits of randomization by de-randomizing the bounds, in the sense that I've shown you bounds on the expectation of the posterior, but we need 3 hours really to cover that. But there's also a number of bounds which hold for just sampling from that posterior. If I have a posterior distribution, I can use actually things which are much more exciting than just the mean. I can sample from that distribution. I can look at the median. I can look at quantiles of that distribution. And there are Backbase bounds for that. So there are bounds directly for those randomized objects, which are not holding for the expectation of the posterior, for example. And there are other series of bounds. There's a few papers lately, and we do have one actually exactly on that topic, which is here. So the title doesn't appear, but it's margins and de-randomizing. Yes, this one. Margin and de-randomization in
That's right.
Backbase.
Yeah.
And that's exactly what we want to achieve. You have a bound. So the price to pay for that is an extra term in the bound. But basically, if we can de-randomize the bound and go from the expectation with respect to posterior to just a single realization of the posterior, it matches much more closely what people actually do in practice. People obviously never compute expectations for neural networks. They just compute point-wise estimates for the weights.
Okay.
I hope that answers the question.
Yeah, we've got one more. Eunice is going to give one more talk. Can I ask you? So I'll let him do that, and then maybe we'll move the discussion to the breakout rooms, and maybe you'll join us in one breakout room, perhaps. Yeah, great.
Very happy to, of course.
So let's see, Eunice, would you like to ask your question now? And this
yeah, sure, if there's time. So my question was just, we got interested in this PAC-Bayesian approaches. We had done some problem where we had some randomized algorithm and we had some PAC bounds. And then we got interested in these PAC-Bayesian bounds, and we wanted to apply one of the results that we got there. And this is actually where my questions comes into play. So, so because of the divergence terms that you mentioned, for example, DKL, aren't we not limited to only distributions then for which we can compute this divergence? And isn't it more computationally costly also to because we want to minimize some Bayesian risk, so we need to compute it. So that means that we have to first compute the classical empirical risk, then integrate it against whatever posterior we've chosen, and then minimize that. So isn't that actually more costly and more like takes more time to reach a solution rather than just integrate with just to minimize the classical risk?
Yeah, that's a great question. Thank you very much. I'm delighted to hear that you're gaining interest in Backbase. You're right when you say that actually the choice of the KL is motivated more by mathematical comfort probably than computational fizziness, in the sense that of course you can compute, so you get an exact closed form of the KL in some settings. For example, the prior and posterior are both Gaussian, then you get a closed form for the KL and you can directly compute the value in the bound. What is happening in most cases is that we do estimate the KL because resulting to Gaussian prior and posterior is not so satisfactory. Again, if you keep in mind the movement I was mentioning earlier about this model-free, trying to get rid of pretty much all the assumptions in Backbase, I like to call this agnostic learning, in the sense that we don't want to be constrained by assumptions which are actually statistics 101 assumptions, because we need them to make the theory work, but it doesn't mean anything in the machine learning world. So if you keep this in mind, using Gaussian distributions just to make the KL tractable is certainly not extremely satisfying. So there's a number of contributions in which the KL is actually expanded to more interesting terms. I'm thinking about MMD. I'm thinking about the F divergence I've just shown briefly. There's another paper from people in Quebec on the Rényi divergence. And my overall answer would be, it's not always the case that you can have a tractable form of a complexity term, but if you can approximate it and have a reasonable idea of the quality of the approximation, it's often enough. In the sense that if you have a good reason to believe that the location of the minimum of the right-hand side term is the same both for the closed form of the KL and the approximation of the KL, if you run just a Monte Carlo approximation of the KL, which you can always do, then you have a good reason to favor the approximation of the actual computation of the KL. If you think about computational costs, the Monte Carlo approximation is costly, of course, but if you think about computing the KL between two Gaussian and very high dimensions, this is also costly, right? This scales very nicely with the ambient dimensions of your Gaussians. So I don't think many people are using the computational trade-off to decide between both. It's mostly for mathematical reasons. Does that make sense?
Yes, yes, it does. So I'm concerning actually also integrating the empirical risk with respect to whatever posterior you chose, whether it's a Gaussian or not. Like, it also, creates extra computational cost.
So it does create extra cost because you need to approximate this. Obviously, if you knew the closed form of the expectation, there would be a little problem. But the risk you might be facing is that the bound becomes overly conservative, right? Because you're no longer considering a realization of the posterior, but rather the expectation of the posterior. So the risk is that the right-hand side term degrades. And as I mean, I didn't spend too much time on this because I didn't have too much to spare, honestly. But if you have a bound so we call this vacuous and non-vacuous bounds. If you have a bound which is true but not useful, in a sense that if you have a binary classification problem, all the errors are between 0 and 1, and the right-hand side of the Backbasian bound is a billion. The bound is true, but it's useless, and that's the risk you might be facing. You might make your bound actually vacuous by integrating with respect to the posterior. I'm very happy to give additional pointers and take this offline if you're interested.
Okay, I think that's a great idea, and maybe we can think about moving to these breakout rooms. Catherine is going to point us to how we can get into the breakout rooms, and we will be back again at 11:30 for the next talk with Peter Tino in the webinar room. So I'll let Catherine talk us to the breakout rooms.